This video is going to take a quick look at the binomial and geometric random variables, which are the subject of the section 6.3 in your book. So the idea here is that you're going to be able to determine whether you have a binomial or a geometric random variable setting. We've already talked about binomial. We will talk about geometric settings as well. You want to be able to make computations about, let's say, mean and standard deviation of a binomial random variable. You want to calculate probabilities involving geometric random variables, and you want to be able to interpret these in the context of the particular problem. In addition, you want to know when you can use a normal approximation to the binomial distribution to calculate the probabilities, something we've already talked about to some extent. So the first thing is to recognize a binomial setting. You can use this acronym BINS. Is it binary? Are the possible outcomes of each trial either success or failure? Sometimes it can mean grouping a bunch of outcomes as success and some others as failure. So for example, when we did the APGAR scores, we said that scores from 7 to 10 represented healthy, and the scores from 1 to 6 represented unhealthy, so that allowed us to create a binary situation. It also must be true that the trials are independent. In other words, when one event occurs, it doesn't have any impact on the probability of subsequent events. So for example, drawing cards out of a deck and calculating the probability that you'll get an ace, that's not binary or binomial because the probability is changing. The number of trials has to be fixed. It can't be some unknown number of trials. It has to be, for example, what's the probability that we'll get 10 heads when we flip 20 coins? So the 20 is the number of trials. And then the success of probability has to remain the same throughout the set of trials. Okay, so as we said, the flipping a coin is a perfect example of a binomial random variable. We flip the coin, let's say 20 times, and we say that in this case probability P is 0.5, and we will call the count X, let's say, of heads as the variable that we're keeping track of, the binomial random variable. And it could have any value from 0 up to the number of trials. So when we're calculating the probabilities, we have to take into account several things. So in this case, we're talking about the probability that in a given case that the parents have a 0.25 probability of having a child with type O blood. And we want to say, what's the probability that P of X is equal to 2, where X is the number of children who have type O blood out of 5 children. So 5 trials, probability of 0.25, and number of successes that we're looking to find the probability of is 2. So we can pick one particular configuration. So let's say we have success, success, failure, failure, failure. We multiply the probabilities, 0.25 times 0.25 times 0.75 times 0.75 times 0.75, which gives us 0.2637. However, we could have had those 2 children with type O blood in a number of different configurations. We could have had success, failure, success, failure, success, failure, failure. We could have had failure, failure, success, failure, success, etc. It turns out that there are in fact 10 different ways that we could have that, 2 with type O blood and 3 without. And so we have to multiply our 0.02637 probability by 10, which gives us an overall probability of this occurring of 0.2637. So the way that we calculate that 10, which we call the binomial coefficient, is like this. So the top number in this is the number of trials, factorial. So for 5 trials, it would be 5 times 4 times 3 times 2 times 1. The bottom, the 2 numbers down here, k is the number of successes, and then we have n minus k. So for example, in the type O blood setting, k would be 2, so we'd have 2 factorial, or 2 times 1. N minus k would be 3, so we'd have 3 factorial. So we'd end up with 2 times 1 times 3 times 2 times 1 as our denominator. By the way, 0 factorial is defined, and it is equal to 1. So when we put all these things together, we get our binomial probability formula, which consists of several parts. The first is the number of arrangements, which, as we said, is this, we call it n choose k. So in n trials, how many different ways can we have k successes? Then we have the probability of k occurring, which is p raised to the k power, and then we have the probability of k not occurring, which is 1 minus p, and that has to be raised to the n minus k power. This gives us our binomial probability formula, and this is what your calculator can do in one calculation with binomial CDF. Okay, so when you're setting up a problem like this, you want to state the distribution and the values of interest. So indicate that it's a binomial distribution, indicate the number of trials and the probability of success. And then you perform your calculations and show your work. Either show it, the calculations written out, or use binomial CDF. But when you use binomial CDF, label all the inputs. So you would say, for example, binomial CDF, and you'd say trials equals 10, probability equals 0.25, successes equals 2. If you don't write it out like that, AP will take credit away from you. Okay, so here we have an example, the type O blood, and when we would plug this into the calculator, we would enter in binomial CDF, we would enter 5 for the number of trials, we would enter 0.25 for the probability of blood type O, and we'd say, let's say 3 as the number of successes if we want to find out the probability that 3 of the children will have type O blood. Your calculator will first figure out how many different ways this can occur, which is 5 factorial over 3 factorial times 2 factorial, or 10. It'll then multiply the probability of having 3 children with type O blood, 0.25 to the third, and then multiply that by the probability of 2 children not having type O blood, which will be 0.75, then that number squared. Now, just as with any other probability distribution, we can talk about it based on its shape. We can look at the shape, the center, and the spread. So the measure of center is what we would call the mean or the expected value. And that is calculated simply by multiplying the probability P by the number of trials. So for example, if we did it with the type O blood situation with 5 children, we would multiply 5 by our probability 0.25 to get 1.25, which would be the expected number of children if out of 5 children who would have type O blood. And this is a picture of what our distribution looks like. And so the center, or the median here, would be 1. We can see that in this case, the mean value is going to be a little higher than the median. We have a slight skew to the right. The way that we calculate the standard deviation is we take the number of trials, n, multiply it by the probability p, then multiply that by the probability 1 minus p, and then we take the square root of that, and that will give us the standard deviation of our distribution. So here are 2 formulas. So the mean, let's say mu of x is equal to n times p. The standard deviation, sigma x, is equal to the square root of n times p times 1 minus p. Important point, these formulas work for binomial distributions only. They cannot be used for other distributions. And we'll talk about, that'll come up again in a couple minutes when we talk about when we can approximate something as binomial. Okay, so here's an example of using these calculations where we have 21 students and they're given different types of water to test. Each student has a 1 in 3 chance of correctly identifying the different type of water by guessing. If we're letting x be the number of students who correctly identify the cup containing the different type of water, we want to calculate the mean and standard deviation of x. Mu of x equals n times p, which is n is 21, number of trials, 1/3 probability. So 7 would be the expected value of this distribution, or in other words, 7 is the number of students we expect to guess correctly. The standard deviation we calculated as such, and we ended up with 2.16, which means that if we did this repeatedly, typically the number of correct identifications would vary around the mean of 7 by 2.16. So go down to 7 minus 2.16 or 4.84 and up to 2.16 plus 7 or 9.16. So that's where we would expect most of the guesses to be. Okay. So binomial distributions are important when we're talking about things like surveys and sampling, and we're trying to figure out the proportion P of successes. So for example, you are surveying people about whether or not they support some gun control initiative. You're going to have people answering either yes or no, and so that represents a binomial setting, because, or at least a binary setting, because the answers are going to be either yes or no. So in sampling, one of the problems is that you're never going to have a purely binomial setting, because when you sample someone, you are sampling without replacement. You are not putting that person back into the population and giving them a chance to be chosen a second time. So strictly, it's not binomial. However, the calculations will be close enough to a binomial setting that we can use a binomial approximation as long as the sample size is less than 1/10 of the size of the population that we are sampling. It's somewhat arbitrary, but basically that's the rule of thumb that we will use, and it'll make everything much simpler because binomial calculations are a lot easier than if we did not use the binomial calculation. The other thing that we've talked about is that as n gets larger, the shape of a binomial distribution becomes increasingly close to a normal distribution with, again, mean of n times p and standard deviation of square root of n times p times 1 minus p. So we can use a normal approximation of a binomial distribution under certain conditions, which is when n is large enough and when p, or at least a combination of n and p and 1 minus p are large enough. As p approaches 0 or 1, our distribution will be less normal. When n is smaller, our distribution is also less normal. So the rule of thumb we use is that as long as n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, we can use a normal approximation of a binomial distribution to do our calculations.